Alright, so today we're going to have some notes over the Earth's structure and plate tectonics. Okay, so your different learning goals you have. First of all, you're going to be able to explain the causes of convection currents. Secondly, to explain how rock layers are affected by motion inside the Earth. And lastly, you're going to be able to explain the cause and effects of earthquakes and volcanoes. Okay, so the Earth can be divided into as few as three areas: the core, the mantle, and the crust. We've actually taken it a little bit farther than that and gone a little bit more in depth, but basically there's three parts: the core, the mantle, and the crust. The crust is the outermost layer. It can be as thin as 5 kilometers thick or as thick as 100 kilometers. This picture here in the middle, you see you have your distances or thicknesses. Under here you have the mantle. Here is a picture of the continental crust, one of the continental crust. You can see how thick it is compared to this dark brown oceanic crust right here. This moho I can't say that word. Moho discontinuity. We will talk about that later when I get back. Down here at the bottom, this picture, so the continental crust right here is 2.7 grams per centimeter cubed. That's the density of a continental crust. Oceanic crust is 3.0 grams per centimeter cubed, and you can't see this because it's not recording it, but the mantle has a density of 3.3. So if you remember from way back when we talked about density, the denser items tend to sink and the less dense things tend to float. So the green, which is your mantle, has a 3.3, oceanic crust has a 3, and continental crust has a 2.7. So those things do, the most dense is on the bottom and the least dense is on top. So the mantle is our next layer, and it's the layer between the crust and the core. The mantle contains the majority of the mass, which is the amount of matter, of the Earth. No one has ever visited this part of the Earth. The deepest we've ever drilled is something called the Kola Super Deep Borehole in Russia, and it reached a depth of over 12 kilometers. That's over 7 miles deep before having to stop drilling because temperatures reached over 300 degrees. This was done way back in the 80s, probably before you all were born, but that's the farthest that we've ever been, and that's only 12 kilometers into the crust. Okay, since we have never been to the interior of the Earth, scientists have to make their conclusions about what's inside the Earth based on observations of the surface. Some of those observations come from seismic waves, from earthquakes and tsunamis, and things such like that. And we'll talk about that more in depth later. Okay, the last layer, the innermost layer, the core, it's the center part of the Earth. And this part of the Earth, they believe, is where the majority of the Earth's iron and nickel, which are very heavy metals, are located. Okay, so that was just a very basic overview. Now we're going to get into more specifics. So the physical structure of the Earth, and you kind of drew this a little bit with our project the other day. So if we start at the center and work our way out, you have the inner core. The inner core, shown down here in yellow, the inner core, they believe, is the solid, dense center. It's believed to be solid because yes, granted, the temperature is so high, but there's also part of the temperature is because, because it's the center of the Earth, and also because there is immense pressure from all of this stuff pushing down on top of it. The pressure is so dense that it's not allowing the liquid to expand, so it's actually forcing it to become a solid, so it's compressing it into a solid ball. Around that, you have this kind of peachy orange color here, and it is the liquid outer core. So this one has a little bit more room to expand, so this one truly is a liquid. Next, you have the mantle, and the mantle can be divided into different subsections. You have the mesosphere, asthenosphere, and lithosphere. This is where you're going to find all the magma. The mesosphere, or the lower mantle, is a thick liquid. It's the closest one to the core. Next, you have the asthenosphere. It's kind of a plasticky type consistency. It's not quite liquid, but it's not quite solid. This part of the mantle, it is cooler here, but basically it's a solid substance or a rock that's moving very slowly. And we'll talk about that motion in just a second. It's kind of, I think of it like a plastic. When it heats up, it kind of warps. It's still a solid, as in like you could set some stuff on it, but it's slowly changing. The uppermost part of the mantle, the part closest to us, is called the lithosphere. And remember, we've talked about the prefix lith, meaning stone or earth, and sphere, meaning circle. This is the part of the mantle that is very rigid. There are two parts to the lithosphere, the crust and the tectonic plate. The lithosphere is the part of the earth that is basically all cracked and divided into different sections. Those cracks and divisions we call tectonic plates. So here what you see is a picture of the tectonic plates, pieces of lithosphere that are broken down into pieces. And what they do is they float on top of the asthenosphere. And yes, they do move. So you can see here in the colors, here you have the Eurasian plate, which is part of Europe and Asia, for those of us that still have issues with our continents. Down here we have the Australian and Indian plate. Here's India, here's Australia. The Antarctic plate is at the bottom, because it's for Antarctica. The Philippine plate is right here. This big one right here is the Pacific plate, and we'll come back to that in a second. Up here in the green you have the North American plate. There's one right there in orange. The Cocos plate is right here, kind of small. This one right here is called the Nazca plate. You have the South American plate. Here's the Caribbean plate. Remember Haiti a few years ago? Here's the African plate. Down here is the Scotia plate. Okay. Alright, so tectonic plates, they are made of one or both types of crust. And there are two types of crust. There's continental crust and oceanic crust. Has nothing to do with pizza crust. We're all talking about rocks right now. So the continental crust, if you look down at this picture right here, you can tell that this is thicker. It has land on it. This is where we live, and this is what you see on the earth. Oceanic crust you are not going to see unless you can get into a submarine and go down to the bottom. Oceanic crust is thinner and it has the ocean sitting on top of it. Okay, so it is going to be denser because you have a whole lot more weight pushing down on it. Okay, and you'll notice these arrows right here, the darker arrows. We're going to come back to that in a second. The lighter arrows here, the white ones, notice those going down right there. Those, we'll come back to those in a second, but remember, arrows on a diagram indicate motion. Okay? So these things move, right? Yes. The theory that Alfred Wegener, I think that's how you say his name, came up with is called continental drift. Basically, there's lots of evidence, and what he said, there's lots of evidence like fossils, the same fossils here on North America as there is in Africa, things like that. And there's lots and lots of evidence out there. But he basically came up with this hypothesis that all the continents at one point in time were together in a single landmass, and he called that Pangea. I'm sure you've probably talked about that before. So how do all these giant things, or giant pieces of floating rock, how do these things move? One of the answers that we're going to talk about right now is sea floor spreading. And you'll see down here, you have the North American plate, and then you have the Eurasian plate. The red down here indicates the magma. Again, you have arrows. Remember, arrows indicate movement. And what happens with those arrows is you have this magma that pushes up, and it creates like an underwater mountain range, and those are called ridges. This particular one is called the Mid-Atlantic Ridge. Okay, so if you have magma coming up here through cracks in the ocean, okay, and this is cooling, you're going to have brand new rock forming basically, because as this magma comes up it's going to cool, and you'll notice right here these arrows are pulling this direction. So when you have new stuff forming, it's going to push the old stuff out of the way. Okay, so where tectonic plates meet, um, what you have is you have three types of boundaries. Remember, a boundary is just any sort of area where things contact each other. So there's three of them. There's a convergent boundary, there's a divergent boundary, and there's a transform boundary. Okay, so a convergent boundary is when you have two plates converge upon each other, or they start to collide. A divergent boundary is when you have two plates that are moving away from each other, so they're diverging. Converging means to come together, divergent means to move apart. Transform boundary is when you have plates sliding past each other horizontally. So how do we know that these things are actually moving, and how fast are they moving? Well, we know that thanks to GPS. Scientists can track the locations of various plates across the globe and track their location changes. They have little GPS stations, and they track the movement of them as the years go. Some of them are moving faster than others. Some of them are moving one direction. Some are moving in an opposite direction. So that's how they figure that out. Okay, so here's another picture of the globe along with the plates. You can see the little boundaries right here. This is where you have two different plates meeting. So the yellow ones you can see by the arrows right here, like the African plate and the South American plate, and the North American plate and the Eurasian plate are moving away from each other. This is where that mid-Atlantic ridge is, where you have seafloor spreading. So that is a divergent boundary, like over here. So you have two plates separating, and you have magma rising and pushing the plates apart, creating underwater mountain ranges. Okay, the purple ones are a convergent boundary. You have those happening kind of on the interior here. The Caribbean plate is one right here. There's one right here off of Mexico. Up here off the Aleutian Islands in Alaska is a convergent boundary. So you have two things coming together. When that happens, you have a plate colliding and it's diving under another one. Over here off of South America, okay, you have a convergent boundary occurring right here. There's also a huge mountain range right here called the Andes Mountains. Same thing over here. The tallest mountain on the planet, Mount Everest, is in the Himalayas, which are a result of the Indian plate shoving up against the Eurasian plate. So you have mountains tending to form right here. So you have one of them, usually one with an ocean, with oceanic crust, it's heavier. It's going to dive underneath the other one. The last type of boundary is a transform boundary. You have two plates grinding against each other. So up here in California, there happens to be a transform boundary right here, which creates things like the San Andreas Fault. Okay, typically lots of friction formed and things like that. Okay, so alright, so we know that these tectonic plates move, and there's such a thing as seafloor spreading, so you have new rock being formed. But how exactly does this happen? There are three ways that tectonic plates can move. One of them is called a ridge push, which the ridges formed during seafloor spreading is higher than where it sinks into the mantle, so it slides underneath thanks to gravity. So right here you have this ridge. It's kind of like it's a mountain, and everything slopes down. This picture is not the greatest, but it's going to be higher right up in here compared to over here. So it's going to just push itself underneath. Okay. The second way is with convection. Convection currents occur when you have the hotter magma, and this particular one is happening inside the mantle. So you have hotter magma down here that's closer to the core. Remember the old saying that hot air rises and cold air sinks? Well, same thing with magma. Hot magma will rise, okay, because it's less dense. Its atoms are moving faster and things such as that. And the magma up here at the top, closer to the surface, is cooler. So as it cools, it starts to get kind of thick and heavy and dense. So it's going to start to sink. Well, as this happens, you start to create these convection currents. Okay, so as these currents are happening, the same thing can happen in the ocean. The warmer water is up at the top of the ocean towards the surface, and the cooler water is out at the bottom. So you tend to get these convection currents in water as well. And what happens is whichever way this current is going is whichever way it's going to push this plate that's sitting on top of it, kind of like a boat floating along in the water. The third way is with a slab pull. Basically what this is when you have a denser or heavier oceanic crust tectonic plate, and there's a lot of vocabulary there. Whenever you have a tectonic plate, which is the top part of the crust, whenever you have an ocean sitting on it, it's going to be heavy. Think about how much thing of water is. If you have a whole bunch of water sitting on something, it gets really heavy. So since it's heavier, it's going to go underneath the one that it's bumping up into. And as it does that, it's going to pull the rest of the plate with it. It's kind of like when you roll up in the covers on your bed. Whichever way you roll the covers, they're going to go with you. It's all connected. There's no getting around it. Okay, earthquakes occur when tectonic plates push, pull, or slip past each other. And this is not like, you walking by and brushing up against the doorway. It's not that fast. This can take millions of years for a plate to move 12 inches, okay? So you're talking like centimeters or sometimes even millimeters of movement every year. So it can take a very long time. But as you're moving, it's going to create a lot of stress. It's kind of like if you're trying to push a really, really, really heavy box on something really rough. What happens is near the plate edges where these things rub past each other, you get a lot of stress built up. The rocks in the plates tend to deform, so they tend to kind of warp or deform, and basically what that does is it changes the shape of a rock. Elastic deformation. Remember, elastic means it's kind of springy. Deformation means it's deformed. The elastic deformation is going to cause the earthquake. In other words, it's pulling so far you can only stretch, and then next thing you know, it just springs back. Same concept as a piece of elastic. You're going to pull that elastic as far as you can, or that rubber band as far as you can, and it's going to change shape until it cannot do it anymore. So either it's going to snap and break, or it's going to snap and just release the tension. At some point in time, that elastic will release the tension. So what you have right here is a picture from the USGS, which stands for the United States Geological Survey. This is the National Seismic Hazard Map. So in the red is the highest hazard areas for seismic activity. Seismic doesn't always necessarily mean there's going to be an earthquake. It just means there's the potential there. And seismic refers to the type of energy waves that are produced. So you have huge seismic risk in California, San Andreas Fault, and it actually goes all the way up into Washington, and it's actually going to continue up all the way into Canada, and you'll see here into Alaska. Okay, you've got Hawaii here. Anybody know what is, I think it's more like right in here. There's a big national park up in here, which is kind of strange to have this seismic activity right here, because this is like smack dab in the middle of the North American plate. So this is not occurring on a boundary. Or this one down here. In fact, I've read stuff where they've talked about how this has the highest seismic potential for damaging seismic activity out of all the faults in our country. Then there's also one down here. There's also some up in New York, and there's some in Virginia. There's some more there too. So, but these are the highest percentages of hazards of something happening. Okay, so volcanoes. We talked a little bit about the boundaries, which are where tectonic plates meet, and I realize I'm throwing a lot of information at you, but earthquakes occur when tectonic plates meet, and they're just they go to slide past each other, and there's tension created that is released. Well, this type of activity, a volcanic eruption, the majority of them lie directly on a tectonic plate boundary. The Ring of Fire, which is not the whole Finding Nemo thing, there is a phenomena on the planet called the Ring of Fire. And the Ring of Fire is kind of a geographical area surrounding tectonic plate boundaries, and this area accounts for almost 75% of the world's active volcanoes on land. There are a lot of volcanoes that are underwater, and I have videos for you, and I'll talk about that on Friday. So down here, okay, so at boundaries, when you have two tectonic plates meet, especially when you have one diving underneath another one, it is possible for magma to form and rise. It's kind of like getting air bubbles stuck in something. 80% of active volcanoes on land form where plates collide. Now, collide means where they are coming together. 15% of active volcanoes on land form where plates separate. Volcanic eruptions typically are very violent, okay? It is not typical to have a volcano. If you have where plates are separating, it's a slow thing. It's slowly happening. A volcanic eruption where plates colliding, it's another way for it to release the pressure. Okay, so these little triangles represent active volcanoes, okay? The red ring signifies the Ring of Fire. Okay, this particular picture was done quite a while ago. Okay, so to kind of give ourselves some bearings here, this over here, this big tall ridge here, this is called the Mid-Atlantic Ridge, which is what we talked about, how it's forming new land. You do have a lot of active volcanoes here. Okay, now a lot of these are underwater. Here's Greenland, or Iceland, one of the two. There's a big volcano there. In fact, I think that's the one that blew up not that long ago. Here's Italy. There was Pompeii, they think, was buried under ash. Here's Saudi Arabia, Africa. There's a lot of volcanoes in Africa. Okay, then you come over in here. Here's one out in the middle of China somewhere. Here's one up in Siberia. So then, okay, over in here, here's the Philippines. Okay, look at all these here. So you have tons of them. If you just look at the picture alone, the majority of them you see are in this part of the world here. Okay, here's some more mid-ocean ridges. Oops, what did I just do? Okay, there we go. Here's Hawaii, right here, out smack dab in the middle of the Pacific Ocean. Mount St. Helens was the mountain that, or volcano, I'm sorry, that basically exploded half of it off in, I believe, 1980. I was 2. So anyway, okay, so the Ring of Fire is what they call the area. You can see how it does form a ring, and they call it the Ring of Fire because, hello, volcanoes, fire, lava, stuff like that. Okay, so causes of volcanic eruptions. Volcanoes are classified into 3 categories: extinct, dormant, and active. Okay, extinct means they're done, they're dead, nothing's happening. Dormant, meaning kind of like they're sleeping, kind of like they're hibernating. And an active volcano is one that is actively erupting. There's stuff coming out of it. Scientists are going to study active and dormant volcanoes for signs of future eruptions. They're always trying to predict when one is going to erupt. They also study the volume and composition of volcanic gases. Okay, so what you see right here is some links to some different resources about eruptions. On Friday, we'll go through and I have lots of YouTube links to show you guys for these different types of eruptions. Go through and show you these different plate boundaries. But so you have your notes for you. You're going to want to keep those in your notebook. Hang on to those. Actually, for now, put them in your binder. We will go through on Friday after I get some more tape, and we'll actually put them in our notebooks. So thank you very much.